Okay, so I will try to talk about little more on the neutrino detectors. Till now I talked about this only on the scintillator detectors. This is the last two slides of the scintillator detectors or the Cherenkov detectors which use the photomultiplier tubes. There it says that in the reactor neutrino anomaly, it says that if you look for the distance from the different reactors and observed data shows that what is the number of neutrino you are supposed to see, you see this number of neutrinos slightly less than that. This is the some old reactor measurement which is about 10 to 100 meters away. And also there is an experiment, some experiment in the gallium experiment where gallium just put the radioactive material gallium, it becomes germanium and that many how many neutrino you are able to see. That measurement also show the number is less. So these distributions, to explain this, we have to fit, this is the not the three flavor neutrino, you have to go to the fourth neutrino, this is the sterile neutrino, and in the sterile neutrino experiment, if you have the sterile neutrino, so that means the fourth of this neutrino, what is the delta m square and the sine square theta, depending on that, if you fit this data, it will give something like this. This is, I see the few plots, one of the for this reactor anomaly, all these. On the gallium anomaly, if you do the gallium anomaly, then the distribution, and this is the one of the neutrino 4 experiment. This is look for this low length, a shorter distance is called the short baseline neutrino experiment. There it is. And just one summary I just put, all these experiments, short baseline neutrino experiment, these were very short, about 6 to 9 meters or 6 to 11 meters that distance, and it was in the different experiment, different countries, and here is the sum of these features was given. Main thing was shown that the neutrino experiment, what you show, what are the detector technology. All of the scintillators with the liquid scintillators, either gallium dope or lithium doped, that to take these neutron signals, and the many of the experiment is running on just to see the neutrino anomaly. So that means there is a many scintillator based neutrino experiment is going on all over the world. So that's why I spend too much time on this. I will divert a little more on this scintillator based to the other technologies. So, but I start with the scintillator detectors. This again also, this is the liquid scintillator neutrino detectors. It's called that ALS-ND. And once I told these detectors, its principle is 798 MeV proton hit in and low jet mass target, and there are lots of particles produced. One of the particle is pi plus decay to the mu plus neutrino, and mu plus decay to the positron electron nu mu bar, and nu mu bar is source of this experiment is the nu mu bar. It detects to the nu mu bar, and in the scintillator detectors where the inverse beta decay, nu mu bar proton gives you the positron and the neutron again you see these delayed signals. So basically signal in the both E plus and this 2.2 MeV gamma from these NP to D gamma reactions. And here is the some more details of this experiment. I will not go on that detail, but this experiment when they did that experimental, this is this neutrino spectrum, nu E, nu mu spectrum, that is the different flavor spectrum it was seen, and here is this again the summary of this, what is this experiment all together. But the main feature is this, if we look for the energy of the neutrino, it looks for this E mu bar signal, which is short presence is there, but if you look for the data, either if you look for the electron energy or L by EOA, if you look for the energy of that, this blue part, this is the axis of the event it sees. This axis only can interpret it if the nu mu bar transparent to the nu E bar. That is the only explanation was there. So this was this with this other experimental measurement, this was not incorporated with the three flavor oscillations. So that's why the fourth or sterile neutrino concept came. And in the very first day I talked about this, they have seen the signal. Exactly the same experiment was done in the Karman experiment, again Karlsruhe. They did not see this any access, but people take this more seriously and then try to see that this result is right or wrong. Basically in the short distance, nu mu bar oscillate to the nu e bar, and that is happening or not. To do that, they designed a new experiment called the Minibune experiment. It operational in 2002 to 2019. Just comparison of these two. This is the LSND detector, cylindrical detector, photomultiplier readout, and this is my spherical shell cylinders, and also readout by the photomultiplier tube. Exactly the same technique, only here this 0.8 GeV proton beam, here 8 GeV proton beam, so there is little higher energy. And this principle was same. Here in the scintillator detectors, you have again the same scintillators. You have this again the many interactions. You have the Cherenkov ring and scintillated photon signal you will see. So this was the detectors was built just to confirm the LSND result was right or wrong. And then when this is the LSND, this experiment was made, and this is their final results. They look for this quasi-elastic event of the, and then from there they calculate the neutrino energy, and they see some excess of these things, and this Minibune support the LSND results. So that means Minibune was built to tell that LSND result was right or wrong, but the Minibune result says LSND was right. But then still people is at a new experiment. There is nothing, it is not matches with this all other expected result from other experiment. So then to verify this even Minibune, dedicated short baseline experiment at Fermilab with 3 detectors were started, with one of the fundamental change in the detector concept, and that's the main point of my talk or these presentations. So this Minibune, when they see the signals, they see these scintillator signals, and in these scintillator signals, okay, let's which way? As I told you that this my slide is not properly prepared. I may be little bit of here and there. So this okay. In summary, is that if you look for these Cherenkov signals in this experiment, whenever is a signal by gamma, gamma gives this E plus, E minus, this electromagnetic showers, it go forward direction. It will the same signal when this electron gives the signals. They do not able to distinguish, this is the signal is coming from the gamma, gamma is coming from this many interaction. Today morning he gave lectures that where this quasi-elastic scattering, there is many things process can happen, and we do not know many things. Many of the process is unknown to us. That may produce a pi 0 gives the 2 gamma, and gamma signal that can be mimicked, or gamma, the photon signal mimic at the electron signals. So we need a detector which can distinguish the electron and the gamma. Just ruled out that these the extra things what we see, this is not coming from this any interaction which produce the pi 0 or photons. And that the technology was the liquid argon technology. I already mentioned this principle, but this background is this. This liquid argon technology first proposed by Carlo Rubbia in 1977, just after the concept of TPC by Dave Nygren in 1970s. So this was a very old concept, and this concept was used, okay, in short, I just say that this concept was used in the one of the Gran Sasso experiment, the Icarus experiment, just to look for the neutrino oscillations, and it was the old experiment, it was used. And this experiment as a capability to distinguish this E gamma discrimination capability in liquid argon is important to understand signal to background of these new E-like excess observed in Minibune. That was the main point. And I will skip this, these already I explained this principle, but these are the main points that the new E-like signal excess observed in Minibune, this detector can tell that this is really a signal or coming from the pi 0 or other background. So the principle is what it is, what can liquid argon TPC do with Minibune could not. So the Minibune experimental signal is like this Cherenkov light. It is, as I said, if it is come from the electron or this photon gives you the 2 E plus E minus shower, this will more or less overlap. Scintillators in Minibune could not identify it is coming from this gamma or this is electrons. But where is the liquid argon experiment? Here, let's for example, this quasi-elastic scattering happened. It produces maybe a protons and an electrons. On the other hand, it may produce a proton and pi 0. So the pi 0, it decays to the instantaneous 2 photon or this proton and gamma, some gamma. You know the gamma, when it goes, the electromagnetic shower development I told, this gamma will propagate some distance and then it will go to the E plus E minus pair. And this distance is roughly, you call this one radiation length. So on the average, in one radiation length distance, I don't remember this argon, it is roughly about a few centimeters. I forgot the distance. On the average, about tens of centimeters away, we will see these photon signals produced. So this is if we have a quasi-elastic scattering event, then this proton, this is the electron shower will come immediately, and this photon showers, there will be gap. So this allow with a strong photon-electron separation, particle identification across the whole short baseline neutrino programs, and that's the things in liquid argon detectors. We say that again little more on these E gamma separations. Again, this is an microbune experiment. This is one of these liquid argon detectors. These detectors, if the electron signals looks like this side the proton will go, electron will go in these directions. And again, this is the same event, the same thing I showed, but here this looks like that. Here one pi 0 is produced, pi 0 go to the 2 photons, and 2 photon shower is developed in these regions. That's the way. Again, the same thing, here in this proton and then electron, there is no gap, but here there is a gap. So the gap is an important ingredient, and gap occurs, as I say, again, the same pictures. Electron will be showering started, as again repeating the things, the electromagnetic shower is developed, but the signal or whatever we see only the trajectory of the charged particle where it loses the energy through the ionization energy loss. So the electron, as soon as produced, it started the ionization energy loss, the trajectory you will see. But for the photon, it passed through some distance, and after that, it is E plus E minus production, you will see. And then there will be gap, and also in the photons, when the shower will deposit, this in the very short distance, this is the E plus E minus initial phase, the 2 electrons simultaneously deposit the energy. So in the first few centimeter distance, total energy deposit will be much larger, and that was the thing shown here. This is the way, if you look for this energy loss in this very early stage of this where the shower is started, in the early stage, if this is the electron, one of the things we say that there will be gap or no gap. Second thing, if it is the electron, then this electron, we will see the shower energy dEdx 2 MeV per gram semi, that's the we will see. But if it started with this gamma initiated shower, then this energy deposit will be the double. So that's the way, this is the 2 path, one is the separation, and the initial path of this electron where the energy deposit occurs, that will be the equivalent to the 1 electron or 2 electron energy deposit dEdx. That is the way we can identify the gamma and photons. So these are this basic fundamental difference and fundamental concept used in the liquid argon detector, and that's why the big program come in the Fermilab. This Icarus, this detectors is big. It was at the Gran Sasso. It brought to the CERN, refurbished, some upgrade happened. This detector went to the Fermilab, and Fermilab, these detectors now is operational. Along with these detectors, there is another micromolar detector, that's the one thing, and the short baseline neutrino detector. These 3 detectors was made, and with this sequentially some time, it will operated or will operational in this Fermilab. I will show you some geographical position of this, and then at the end in 2030s or 31 we will have a big Dune experiment. So I will talk this few words about all this. And also this experiment, when it is developed, electronics was developed very much. Initially this is a warm readout. Liquid argon, when it is operated, it is the low temperature you have to operate the liquid argon. And then this will be the electronics gradually developed. Now we have the electronics development with this cold at the temperatures we can operate the electronics. That electronics was also developed. Okay, so this is these pictures in this Fermilab. You say that this is the short baseline, this is the neutrino beam, here is all these three detectors were put one by one after others. This is this, all of the liquid argon detectors, I will not show in detail of that. This is the SDNB, microbune and the Icarus detectors, and these detectors is 112 ton, 86 ton, this is the 470 ton detectors, and these detectors was put from the beam line, put a distance 110, 470 and 600 meter. Something like this. If this microbune or LSND result is right, then this oscillation probability of this nu mu bar, oscillation to the nu u bar, that probability will go like this way. So these are the three different detectors. They will try to verify what this LSND or microbune has seen, minibune has seen, is it matches with this or not. These three detectors will look on that. Okay, this is the neutrino beam, and then after that, this is the main neutrino detectors is coming here, is the Dune experiment. And the Dune experiment is this deep underground neutrino experiment at Fermilab, where you will have that neutrino beam, and the beam will neutrino beam. Neutrino beam means basically is the nu mu or nu mu bar beam. They will come roughly 1300 kilometers, 1300 kilometers an hour, and there here we will have these underground facilities. This is this underground facility, deep underground facility. This is the same facilities where this Davis did his first experiment. This is the same mine. Okay, now that was in the small area, now this was the big laboratory, underground laboratory. So here is the neutrino beam is coming, and this is this, if you look for the neutrino beam and a neutrino or antineutrino, this is the beam pattern, nu mu beam. If it is a nu mu bar, then this is this neutrino spectrum, and this is the main range of this neutrino energy, where if at in our delta m21 delta m23 square, that way we say that at this distance this oscillation will be the maximum, and there they will try to study these oscillation properties. And these are the pictures. It shows that if it is a nu mu to nu e or nu mu to nu e bar for this different neutrino or antineutrino beam, and for the different phase of this CP violation phase in this CKM matrix, then how much is the beam, what will be seen in these far detectors depending on these CP parameters. And also, of course, now we know this is the way one is the normal mass ordering, and if the inverse mass ordering, then this distribution will be different. So these detectors was the main goal was to look for this, both the CP parameters, with the CP parameter they can look, but the main goal was also to look for the mass hierarchy. It is this delta M32 is more than positive. It is above, this is the mass ordering. This is this M32, it is above the M12 or the below. That's the things it will look. And this is the near detectors. You have a short baseline detectors. I think I will have the little more pictures on this. Short baseline detectors, there is a three different detectors was put in the short baseline detectors. Here the neutrino beam is coming, and here this is the mainly we'll try to see this, what is the neutrino beam. This is the primary beam, and then in at 300 meters, 1500 kilometers apart, they will see that how much beam will oscillate it. So this is the neutrino beam. There is a three detectors. First one detectors is this, again this near detector liquid argon detectors. So this is the same detector what will be used in the far detectors. This is the liquid argon, same detectors were used. And this liquid argon detector, the size is smaller, I think few meters. So this large long energy muon, if this neutrino produces this energetic muon, it cannot be confined within these detectors. So behind these detectors, there is another detectors. What this is the proposed detectors. Near detector, this is the gas argon detectors. This is the gas, compressed gas with the 10 bar pressure is supposed to operate, and it is in the magnetic field. So when this particle is produced, this is this. We measure the curvature. From the curvature, we measure the momentum of this muon. So this was the one detectors. But these detectors, in T2K, I say that beam was put in the little different axis just to get the oscillation minimum. Oscillation, some energy is to choose the energy, but here also this is the way the beam is goes. In the beam, in the on axis, beam will spread like this. If in this beam is shifted little bit at angle, then these beam properties will be changed. And these detectors want to scan this whole angle of this beam in the different angle, how much the beam. So these detectors can move, and this is another picture of these detectors. These two detectors can move from the beam line with about the 30 meters, and that goes up to maybe the 2.5 degree, which is the beam. And the third detector, this will be always be there. This is the plastic scintillator with the tracker, equivalent magnet. This will always be there with measure the neutrino beam. So this was this concept, but last 3-4 years, many of these revisions, and I think I am not exactly sure that these detectors will come when this 2030-31, these gas argon detectors. Instead of gas argon detectors, there was another proposal of this temporary muon spectrometer. It is a magnetized steel range track for measuring the momentum and sign from the Newly charge current interactions in these detectors. But if you ask me, truly this was too much swapping here and there at this moment. I do not know which one they will come and the neutrino detector will first operational, but they are even still hoping that at the end you will have this near detector, gas argon detectors. So this is the short baseline detectors, and in the long baseline, they will have 4 different big detectors, each one of the 17 kiloton. Again, this is the 17 kiloton liquid argon detectors, but this fiducial volume is roughly 10 kiloton. So this, even though the total mass is 17 kiloton liquid argon, my fiducial volume is only the 10 kilotons for these detector modules. And this is the full experiment. Okay, this is this power and other thing it was mentioning. So this is the detector, 4 blocks of the detectors. I will come little more of this. So this is called the detector number 1, 2, 3, 4. And at this initially when proposal was there, then all the 4 detectors will supposed to come together. But now this plan is that initially there will be 2 modules will come, module 1 and module 2. And this module 1 and module 2, they are not exactly the same, they are slightly different. And those, what are the module 1s? Before coming to the module 1s and module 2, here is something else I just put it. So the liquid argon detectors, I say that liquid argon detectors, this ionization happens simultaneously, this scintillation photon is produced. Scintillation photons we collected to the photomultiplier tube, or here they use the both photomultiplier and the silicon photomultiplier to collect this start time, and then when we see the signals in the anode wires, induction signal, that will gives you the distance. Now the scintillator photon, what it produces, liquid argon scintillator detectors. Liquid argon scintillators, what is produced, this wavelength is 128 nanometers. This is the very UV range. And our detectors, our scintillator, our readout is photomultiplier sensitive to this, our blue, let's for example 400 to 600 nanometer, that range. So this scintillator, this scintillation light we cannot directly use in this photomultiplier. Another factor is that if this is a 120 nanometer scintillators, it goes, this within the medium when it goes, it has a large Rayleigh scattering. I mentioned this first lecture, the Rayleigh scattering. In general, we do not talk, but here they are much bother about the Rayleigh scattering. So this is Rayleigh scattering, the cross section goes 1 by lambda to the power 4. So this, when the small cross section, this attenuation length, I think, okay, how much it is? Somewhere it was mentioned some number. This is this, for this 128 nanometer during the propagation, no absorption. Somewhere I thought number is there. Okay, this number is less than 2 meters or like that number. Now there is an R&D, how we can have this scintillator wavelength, we can increase this little higher. This is the 9 meter versus 1 meters. So this was this 128, it was about a meters, about a meters. Now, if in the argons, here is the some procedures I do without going to much details. If you add a small fraction of the xenon, xenon would be the best, but xenon is the costlier. But if you use the small fraction of the xenon, then most of the 128 this wavelength photon, it will absorb in the xenon and emits an 178 nanometer wave photons. This is like our wavelength shifters were to use in the scintillators. So now in this 178 nanometer, this is the Rayleigh scattering length is roughly 9 meter much larger. So our Dune detectors, the drifting about the 6 to 7 meters, this is the 5 to 6 meters. So in that meter, so here is also there 1 meters. So this 5 to 6 meters, now this attenuation length is 9 meters. So there is a not much loss of the scintillation photons when we go for this 178 nanometers. And here is the one of the places where we directly use these properties of the Rayleigh scattering. So this is the scintillation photons they use. But even though this is 178 meters, it is very far away from our quantum efficiency of our photodetectors. So they have this another technology. This is called this, I forgot the full name, it called the ARAPUCA, Argon R&D and Mass Program of UNICAMP. So in short, this concept, the design concept is that this is in the detectors on the surface. This is 127 or 170 nanometer photon will go there, and a photon will enter there in this. This is the materials. This absorb these energy photons. It emits the wavelength which is the compatible with the silicon PM, the larger wavelength. So this is another conversion happen, and in that conversion, this is this photons in the silicon PM. We collect the silicon PM, and this is the some detailed pictures of that. So this is this two-step way we converted. This is 128 nanometer to first 178 using this xenon just to have the larger attenuation length, and then to have the compatible with this photomultiplier. This is another conversion was taken here. And in the morning class, I think Joydeep was mentioning in this Kamiokande experiment also, the Cherenkov light, they try to use this facility just the wavelength with the scintillator, they absorb these UV lights and they try to propagate it to these photomultiplier tubes to get this little bit more signal. Now these detectors, as I told you, the principle of these detectors, these two detectors, standard detectors of the liquid argon, this is drifted in these horizontal directions, and this is the three wires we collect the signals. And actually this will be the looks like in picture of these detectors. It is 58 meter long, and this is the 12 meter height, this is the 14 meters, and directly in between, this is the way, and here electron will drift this direction or this direction, and in this surface, this will have induction plane where you collect the signals. This is the, where is the cathode, anode, we collect the signals. Okay. So there is some more details of this. This is the standard, but only thing is say 58 meters, this is the big detectors you have to make. And in between, there is lots of R&D of the liquid argon detectors called this dual phase liquid argon detectors. Dual phase means here, when you take this readout of the electronics, all the electronics has to keep in these liquid argon temperatures, and any electronics you put that absorb the energy, so you have to take those energy, those heat also out, and it is the difficult to manage. So in between there is an R&D that these detectors will operate in way. We will have an liquid layers, and top of that there is a little bit of gas layer, gas, or this you say that liquid gas phase. So this liquid electron will drift up to the liquid top level, and then gas phase it may amplify the signals, and there is the gas phase there you can use this my simple room temperature electronics also. There is a lots of R&D went on for this Dune detector for that, but the technology we could not succeed. So that means the dual phase it failed, but they use this technology not as a dual phase, but they take the readout signal in the vertically upward. That is the concept. That's why the second module of these detectors it called these vertical drift detectors. These detectors were to use. So this is this conceptually it is same, only the drift is horizontal direction, vertical directions. And in this case, the readout was taken slightly different way. So for the electron or photon readout, those things also they had to change a lot. So, but the basic concept was the same. Okay, so these are these Dune detectors, the liquid argon detectors. And now I just move to, if you have something to ask in the Dune detectors, you tell me. Now I completely switch to the different topic. Yeah. Yeah. Okay, so wavelength shifting fibers when we talk about, usually yesterday I showed the plastic scintillators. In general, this is the scintillator produced a light. In this microscopic scale, in these detectors, when we doped with the xenon, all the lights what is coming out 178. There is no more 128 almost, no more. So all are 178. Is almost, yeah. Yeah. Okay. Now, okay, again, as yesterday, that's why explicitly said that. When I say initial, this photon is produced neutron interaction, pi 0, gamma, those photons. And thus photon, when it goes, photon goes to this Compton scattering, other effect, or this shower development, electron ion. Electron will, now the electron move, ionization energy loss, that produce the scintillation photons. These photons is few, this is the 1 point, yesterday is my formula, this is 10 electron volt energy. But initially when we started, those are a few GeV, MeV orders. Okay. These are the completely different photons. This we call as gamma and this we call this usually called photons. This neutrino interaction this which is produced, that is very high energy MeV, GeV order. And this is the scintillation photons, it is only EV order. Okay. Anything more? Okay, if not, then I move to completely different topic. Also physics wise also different. There was a discussion so that the neutrino is the Dirac or Majorana. Just to one of the answer it can be given if we have so called the neutrinoless double beta decay experiment, neutrinoless double beta decay. So basically the nucleus, two electron can come, it can go to this A and Z will change and then two neutrinos come. This is the very common many nucleus we have. But that nucleus can also have this process, this is the two electron, if this part neutrino and is its own neutrino antino its own antiparticle, then maybe this is the chain can happen, then it will have a two electrons, no neutrino. So now in these transitions, fundamental difference between these two beta 2 nu event, it's like in our standard beta decay experiment, what is the energy spectrum. But if it is go to the neutrinoless double beta decay experiment, then this is the total energy, sum of this energy of the two electron is this in a mass difference of these two nucleus. So that means we should see a peak at this point. And this is the zoomed view. This is this we call the neutrinoless double beta decay experiment. This is this bit we can see. And this is many experiment and the last many years it went on. I may not go to all these details. So these detectors it was okay. Now if we say the nuclear form factors and phase factors, mass of the neutrino, everything, this the width of these two neutrino is go to the phase factors q to the power 9 and the geo neutrino is the q to the power 5. So this is the way it goes. So most of the cases this is the event was dominated by this 2 beta 2 neutrino event, and this in theoretically if I say that how to use this, if you see this neutrinoless double beta decay, m beta beta is nothing but a sum of mi ui square and mi plane. If the neutrino has this normal mass hierarchy, then these two planes, the data point should be with this existing constant, it should be like this in these regions. If it is an inverted hierarchy, then we may see within these regions. With this neutrino-less double beta decay, m beta beta, that way you can reduce gradually you can reduce this constraint. So if we can give the constraint that this mass will be smaller than this, then we can reject these inverted mass hierarchy options. So that's why the many experiments last many years. Okay, this is the way we can inverted or non-inverted, but the main thing is that is it a Majorana or the direct neutrino? So do the experiment. And this neutrino masses. This is the lowest neutrino masses, minimum one mass. How much is the mass? This is the Cartan sensitivity. If time permit, I may show 1 or 2 slides of that also. But this is the some boundness coming from the Cartan. So this is this main motivation to look for the neutrino-less double beta decay. Again repeating, it is Majorana versus Dirac, or it is that interpreted in terms of this my inverted or normal hierarchy. Using this result, we can tell it little bit. So there is many candidates of this neutrino-less double beta decay. And when you measure this, what is the lifetime limit we calculate, it depends on the mass, time, what is the energy resolution of the system, background rate, acceptance, and some constants. And in this neutrino-less double beta decay, if you go for the different sources, germanium, xenon, tellurium, cadmium, the many sources are there. They are chosen for the different experiment. It based on what is their abundance, what is the relative abundance among, these are all the isotopes. This what is the relative abundance with respect to the two isotopes, how to make them, and what is the energy of that energy of we see. Depending on this, all these criteria, different experimental choices of the different range. And depending on the different energy range, and also you have to see that in this energy range is small, this is the uranium-238 radioactive dominated area, so this range. And this is this boundary range end of thorium-238 gamma radiated, this is the range. So if you look for this within this range, these are the background will be larger. If you go for this range, then this is our uranium-238 beta radioactivity, that background will be dominated. But if you go higher side, those background is less. But now you have to see that other factors, what is the abundance and how you can prepare the samples, all this. So that's why neither of them is ideal. And I think this story I used to tell this story everybody, so let's see, I tell this story to you people also. This is the story of this Syed Mustafa Ali. How many of you know him? He is a Bengali writer, and he is the other way, he was the first base of Humboldt Fellowship. But he went to the Humboldt Fellowship Germany with this Bengali in the literatures. So once he went to a doctor in Berlin, in his story he mentioned this way. So he said that I have cold and cough. Can you give a medicine? Doctor is known to him, explained. Doctor says, yes, I will give you a medicine. So he was a little confused and he said, the doctor, means not the doctor, his friend, he said that, yeah, in Bengal we used to know that for cold and cough there is no medicine. So doctor said, who said there is no medicine? You see, this is Almira, he showed an Almira. So all this medicine, all the medicines are for cold and cough. So he was even more confused. So many medicine and there is no cold and cough. So he was surprised. Then his friend says, you know, if there is any medicine for cold and cough, there would have been only one medicine. These are the so many medicine because nothing is cured. Nothing is cured this, so something is used curable here, something is there, so we put all this medicine. So this is the standard example. I see all the cases when you see this more than one option for something, you will see that neither one is perfect. If anyone is perfect, everybody would have gone through that one. So that's why there is not many things. Here is the different, this is the different of these isotopes. And again I put this, what is this energy level available? And then based on these isotopes, there is a many different kind of technology which uses scintillator based at the low temperature, the scintillating light of the crystal, the low temperature technology, semiconductor technology, loaded scintillating liquid technology, time projection chamber, some of the tracking device, and some of the solid scintillator was used for the different experiments. And for the different experiments, here is I put a list of the experiments. There is many experiments went on and planning in these coming days just to look for the neutronless double beta decay for the different sources using the different technologies. So I will try to go through this. One of the technologies, one slide of these 5 of the different technologies. What happened? So in short, this is the technology was volumetric technology. These are the 3 experiments was for this. This is volumetric, is that measuring the temperature. This is they try to measure. Semiconductor detectors. This was the measure. Garde was one of the experiment. Is coming experiment the legend. Scintillator detectors. It was a Cumberland experiment, a snow experiment. Initial goal of this experiment. This was more or less a success. Their initial goal. Now they extended this their experiment to look for the neutronless double beta decay. And the time projection chambers, this is the XOR next. This is the time projection. Again, it is the liquid argon time projection chamber or this liquid xenon time projection chambers. So that's the things. And the tracking calorimeter, which is more or less the conventional collider experiment kind of thing. This is completely different technology than all of this. And of course, this list is not an exhaustive list. And this is the other way people group this neutronless double beta decay experiment. This is the brute force way just to see signals. And this is the peak sequencer signals where you look for the signals with this peak of these 2 neutrino at this point. This total energy sum should be here. This is the experiment. And this is this what I say that conventional to the collider experiment, the detector. They try to track this is the 2 neutrino, 2 beta particle within the detectors and this try to visualize, yeah, this is the real signals. Okay, let's see. So the QPIT, this is this Curie upgraded with particle identification. Okay, this is the volumetric detectors. This is the, so the next generation double beta decay replaced the Curie tellurium oxide with 1596 lithium molybdenum oxide. So here molybdenum, that is this my double beta decay that source. So this is this roughly we say the 240 kg of molybdenum. So without going in detail what it is, this was put in the cryostat. Here is all our small sensors, and sensor is that these are the sensors. Sensors where this, if this is the double beta decay happen, this is that neutrino or 2 beta decay will go the beta decay, they will deposit the energy, and in this case that when they deposit the energy, the temperature will change. With the thermal sensor, they will thermal bath is connected. So this when this is that suddenly the temperature will change, this thermal sensor will notice it and detect the signals. And also this scintillator, this will produce a light. There is we put an extra detectors to measure the light. So it's the QPIT we say that heat plus light. And the previous detector it was only bolometric, it measured the temperatures. So that's the way it will try to see these signals of this molybdenum decay. And this is the some limit and other thing. I think next week Professor Bandra Nanal will talk much more about the physics goal and other thing. I just say this technology of this. So this is this detectors will use, it is not used operational yet. So this is this with this thermal sensor and the simultaneously detect the lights, and this detectors were put in this what we call this refrigerator. Okay, this is the completely different way the meaning. And if you go, actually it is happening even TIFR itself. When people say that I want to buy the refrigerator, it cost 2 crore, people are surprised. So this is the different technology. Basically this outside the temperature was controlled, go to the up to 50 millikelvin temperatures, and it goes in the 4 or 5 different stages, and this concept is used for many experiments. So this is this very technology challenging. Okay, I have another 10 more minutes, I hope. And this is this, okay, scintillator signals, how we'll see simultaneously if we see for the light and the sound, how you can distinguish this is other background. These are the some pictures. Okay, then this is the limit. Second one, the legend. This is again, this is Grant-Sasser experiment. This was the based on Vizard of Gardner detectors. It is nothing but in silicon sensors. What I say that reverse bias silicon sensors. When the silicon sensors, so there it is embedded that sensor itself in this sensor itself. It is just my double beta decay source that we put, and this is the sense. This is the signal, the double beta decay signal. If for this some other signal come, the two different point it will signal will come, that it will try to distinguish this. So this I say that it is the based on the Majorana and Gardner technology. What is the technology? It says Majorana, it has a technology of the small sensors, and this is the electric field line, and the color is say that my weighting field, that strength. Okay, this time I did not talk, but in the preschool I talked about the electronic signal. When I take the signal, it is we take the Ramos theorem formula. It is the product of this movement of the charge plus the weighting dot product of the weighting field in the sensors. And so in this case, only these reasons the sensor was much more sensitive, other reason it is not. And in this case, this technology was slightly widened. But in the legend, this technology both were they combined, and they could have the big sensors where this my depletion region is much large area is much more sensitive detectors. Basically, this is, you can think about simple reverse bias PN junctions, but the technology was developed such that my weighting field is much covered in the larger area, so this I can see the signals in the larger area. That is this main point here. You say that enriched germanium, p-type cointactors, so Board energy germanium, inverted coaxial point, conducting detector, event topology, active veto, all the jargon is used. Eventual concept is we have a very large detectors where this is the sensitive to detect this my double beta decay. And also these detectors when we put, and this is the detectors that will see the signals. And also again these detectors was put in this low temperature, and for external shielding, this is the wavelength shifting fibers they put, try to see to veto this any other kind of background, and this is my detectors, sensitive detectors. Then this third one is the Kalman detector. It is a liquid scintillator detector, so 1 ton I said. And then in the scintillator detectors, in between the balloon, they put, this is the 136 xenon in here. So that's the thing, when the 136 xenon, this is gives you this 2 beta that signal, this scintillator, this photomultiplier in these detectors, they will see the signals. That is the way they will identify this from where the signal is coming, and the total sum of the signal, if the neutrino-less double beta decay, it will peak in a particular point. So in that's the way they will try to identify if there is an interaction happen within this point. And Kalman-Giant, it's go many way. 2011 to 15, it was about that 400 kg of xenon. Then it go to the 750 xenon, and then now it is I think already operational with the 1 teraohm of xenon detectors. 1 teraohm of xenon in between this. Okay, and then this is this NXO single phase 136 xenon detectors. So this is this liquid xenon time projection chamber. So this is the detector picture, okay, readout part. The detector is something like this. Here is the liquid xenon. When there is some signal will produce with the silicon PM, the photomultiplier take this when the signal is started, and then this is the time projection chamber. Time projection chamber, this is the electron what it will produce. They will drift it to this again this cathode, and this picture says, in this time projection chamber, this is the readout electronics where they will see this induction charge grid, and behind the induction charge grid they have the silicon PM where they will see the light. So that this light, it will see this induction charge grid there. First when the light will produce, when the charge particle pass through, that signals one they will see, and then when this is the ion will come to here, then they will see the induction charge signals. So that is the second signal gives you the time, and that means where the signal is produced, and then from that total charge they can measure the total energy of the signals. So this is this NXO single phase detectors is used for the TPC. Okay, this is the time position chamber. In this preschool I showed these pictures. And then this is the next detector. This is the detector is this high pressure gaseous xenon detector. Earlier on the liquid xenon, this is the gas xenon detectors. These detectors, the gas xenon has the advantage. Again, this is the same principle. If there something is happened, there is a scintillation light will produce, we will see the light signals and the electron will drift here. In the gas, in these regions, electron will be signal will be amplified with this electron multiplier in these regions. And in this multiplication, this electron means multiplication of electron will collide with this another gas atom, excited, de-excited. They are also produced another second electronic signals. And the second photonic signals, that signal we will see in the later on. So typical picture like this. We will have initially when this particle, the beta particle will go, we will have first electronic signals, and then when electron come to this point, and at that avalanche is happened, and there this is the large signal will produce, we see the secondary signals. And now where the signal is produced, if I have this photomultiplier tube properly, I can track down this particle. This is an example of the 2 beta going from starting from here to here and here to here. At the end, particle momentum is very small, there the energy loss will be more. That's the way I try to identify this is a muon trajectory in this time projection chambers. And my last one is the NEMO detectors. This is the Neutrino Majorana Observatory. Again, this is the detectors. This is this little complicated. This is the detector. So this is the cylindrical difference shell of the detectors. And if I see from the top, this picture is something like this. These detectors, here it will be more easy to explain. In the middle, we have my double beta decay source foil. And inside and outside these regions, we have this is this tracking device where when the charge particle pass through, it lose the energy, and with the straw tube or the tracker detectors, we will see where the particle is gone through. And at the end, we have a calorimeter where we measure the total momentum of the total energy of the charged particle. And here, these trajectory signals also put in presence of the magnetic field. It was the magnetic field. Magnetic field is not very large, and this detector is length is about 3 meter, diameter is 2 meters, and this magnetic field is not, and this is the source is the this foil and 6.9 kg of molybdenum, and this tracker is 6180 open drift cell anode wires. Like this is the preschool time I showed you this kind of pictures. This is the kind of in my anode wires where the particle will go anode wires, you collect the signals. This is the field line near the anode wires. Similar to that, not exactly that. And using the anode wire, I can make the position of this x, y on z coordinate. Z coordinate position measuring mainly the wire charge division method and other method we can measure. And also, and then eventually you are supposed to get this kind of a signatures. And this calorimeter part, this is the scintillator, this is the put 1940 polystyrene scintillator. It is not that. This is the polystyrene scintillator yesterday what I showed, that the polystyrene scintillators and kind of a scintillators and read out by the photomultiplier. It gives some energy resolutions and the time measurement is giving the 5 picosecond. So these detectors is supposed to get this kind of signals when this neutral is double beta decay, particle will bend, and this is another direction, another particle will come, and calorimeter it will deposit the energy, and these two energy sum should be the sum of these two beta. That's supposed to give you the signals. So this is the detectors, and now I'll end with this point. I just show all the detectors, but as I mentioned that in Kamiokande experiment, any detector we made, what are the signal we see the detectors? Is it right or it's coming from the sum of the background? First of all, the signal is coming from the sum of the background beyond our understanding or not, we have to verify it. And that is this is the example I am just showing here, but this is true for all the other few example I just mentioned, everywhere they try to follow. So these detectors, they said that the 20 sectors was divided, these 20 sectors was divided. In the 20 sectors, only I think there's a 15 sectors they put these neutrino double beta decay sources. And the remaining part, they put the different sources. So that's all these are new beta source used for calibration. These are the known source which decays, we know it decays to the 2 neutrino 2 beta. So that I know the 2 neutrino 2 beta decay, and some of the sources here this in the sectors 1.5 sector, these are this color, natural tellurium with 6.1 kg tellurium, and one sector is the pure copper, means there is no neutrino less, nothing, no beta decay. So in these sectors, if you see some signal, this is coming from only instrument. That's the way you try to suppress the instrumental background. If there is some beta decay background, they will subtract it from these sectors of the data. So this was used for all the, as I said, calibration was done using these sensors where we do not expect to the neutronless double beta decay, and that time what are the signal we see? One, where is the copper, we said that is this by intrinsic noise of the instrument, and second, when is the new beta, that what is the sensor signal I see, that way I can calibrate all our detectors and say that correspondingly what are the signal, expected signal we see from this, and that way I will calibrate our detectors. Okay, so that's the thing I want to end, and I have 2 minutes time. So you said I will not show much, only I say the neutronless double. Okay, this is not the physics I will say. I will say this another experiment was there, how to measure the neutrino mass and the beta decay spectrum. Depending on the mass, you see the what is this energy level at this end. Depending on the mass, the tail of the distributions varies. So if you measure the tail of the distribution, you can measure the mass of this. If you measure the tail of this beta decay, you can get the mass of the neutrino. So again, this neutrino measurement, there's also many different sources and many different options. One of the main experiment is a cartoon experiment. Okay, I will not go in it. I just I will not talk physics. I'll just say that these detectors was a very big detectors. These detectors was built in Munich, and it was supposed to put in the Karlsruhe, and this is the Karlsruhe and this is the Munich, and these detectors when it's built, it go through, these are the path to the journey to bring it here. Means you are making an instrument, it does not mean that you just shift from here to here. And as I told you this, my hyperconjugate filling the water will take these 8 months. This is nothing, no physics is there, but this is the 8 months is required. And this is also, if an instrument is ready, it does not directly shift it a few hours from here to here. It has to go to the many steps to come here. And even when it go to this was one of the pictures I will just show you. This is the pictures. It goes to one of the village road. They take this way, between the village, this is the detector is moving. Okay, this remind me the another old story. This is the kind of same kind of experiment. Detector was in old LEP experiment, that Delphi experiment. There one of the detector was moved from one side to the sun, and they have this road map. Everything was mapped, everything was checked. It was perfectly fine. It was moving, and during the measurement, during the transport in the road, they put the extra layer of pitch, and they had blocked it in this one of the bridge, that instrument. So you keep in mind all the things when you do the experiment. You may see this like many unexpected scenario. So any experiment when you start, most of the big experiment always some delay and other thing. Most of the reasons are all these reasons was unexpected. Okay, I think that's all. I'll stop it here. And just one of my point, as I told, I take roughly 60 to 70 hours to give these lectures for this matter particle interaction and particle. In 4 hours I gave you. I am sure it is nothing I could convey, but you are welcome anytime if you can ask me the question. Thanks.